How can you know where a planet will be 100 years from now? Not estimate, not guess. No. For much of human history, such certainty would have seemed impossible. The world appeared ordered, but that order was interpreted rather than demonstrated. Motion could be described, but not fully explained. The heavens followed patterns, yet those patterns seemed to belong to a different realm than the one on Earth. What moved above appeared governed by principles distinct from those below. There was no single framework capable of unifying these elements into a coherent system. The universe could be described, but it could not yet be reduced to law. This distinction is fundamental. To describe is to observe what happens. To establish law is to define what must happen. A world that can only be described remains open to interpretation. A world governed by law becomes predictable. In the 17th century, this began to change. The question was no longer simply what the world looks like, but whether it could be expressed in universal, consistent, and mathematically precise terms. If such a description were possible, motion would no longer be merely observed. It could be calculated. Forces could be defined rather than inferred. The behavior of objects, whether falling toward the ground or moving across the sky, might follow the same underlying principles. In 1687, a work was published that gave this transformation its most complete form. It did not simply describe the world. It presented a system in which motion, force, and gravity could be expressed through universal principles, applying equally to objects on Earth and to bodies in the heavens. With this shift, the universe ceased to be merely observed. It became something that could be known in advance. Before the universe could be expressed as law, it had to be understood in parts. For centuries, the dominant framework for understanding motion and the natural world was shaped by Aristotle. In this view, the behavior of objects was not governed by universal principles, but by their nature and purpose. Heavy objects moved downward because it was their natural place to do so. Lighter elements moved upward. Motion was not something imposed by external forces in a consistent way. It was something that reflected the inherent qualities of matter itself. This way of thinking created a world that was coherent but not unified. Different types of motion required different explanations. The movement of a falling stone was not governed by the same logic as the motion of celestial bodies. The heavens were considered perfect and unchanging, moving in precise, circular paths. The Earth, by contrast, was a domain of irregularity, decay, and imperfection. As a result, there was no expectation that a single framework could explain both. By the 17th century, this structure began to show its limits. Observations became more precise. Instruments improved. Astronomers could track the movement of planets with increasing accuracy, revealing patterns that did not fully align with inherited models. At the same time, thinkers such as René Descartes sought to reorganize knowledge itself. Descartes proposed a universe that operated mechanically, governed by matter and motion, rather than by purpose or inherent tendencies. In his view, the natural world could be understood through extension, geometry, and contact between bodies. Motion was no longer tied to purpose, but to interaction. The universe was no longer interpreted as a hierarchy of meanings, but as a system of matter. Yet even this approach remained incomplete. Descartes could describe motion, but he could not fully quantify it in a way that allowed for precise prediction. His system offered a new way of thinking, but not yet a fully operational framework. The tension between observation and explanation continued to grow. Astronomical data suggested regularity. Philosophical models attempted to account for it. But the connection between the two remained unstable. there was still no single set of principles capable of explaining both terrestrial and celestial motion with the same level of precision. Without universal laws, understanding remained divided. Different domains required different explanations. Prediction was limited. Certainty was partial. The question was no longer whether the universe exhibited patterns. That was increasingly clear. The question was whether those patterns could be expressed in a way that was consistent, universal, and mathematically exact. The problem was not the recognition of patterns, but the explanation of their causes. Why planets followed regular paths could be described geometrically, but not fully explained in terms of underlying forces. Why objects accelerated as they fell was observed, but not reduced to a general principle that applied in all cases. Description advanced, but explanation lagged behind. What was missing was not data, nor even mathematical tools, but a framework capable of connecting motion, force, and regularity into a single structure. A way of thinking in which the same principles would apply everywhere, without exception. In 1687, Isaac Newton published a work that would transform how motion, force, and the structure of the universe were understood. Titled Philosophia Naturalis Principia Mathematica, it did not present a new interpretation of nature. It established a system. At its core was a simple but profound claim. The same principles that govern motion on Earth also govern motion in the heavens. The falling of a stone and the orbit of a planet were not separate phenomena requiring different explanations. They were expressions of the same underlying laws. This was the unification that had been missing. Newton began by defining motion in precise terms. Objects, he argued, do not require continuous causes to keep moving. Instead, they persist in their state of motion unless acted upon by an external force. What had once been explained through purpose or tendency was now described through interaction and resistance. Motion became something that could be measured, compared, and expressed mathematically. From this foundation, he introduced a set of principles that would later be known as the laws of motion. These principles did not describe isolated cases. They applied universally. Whether an object moved slowly or rapidly, whether it remained at rest or accelerated, its behavior could be understood through consistent relationships between force, mass, and motion. But it was the concept of gravitation that extended this system beyond the Earth. Newton proposed that every object exerts an attractive force on every other object. This force depends on their mass and the distance between them. It is not limited to contact. It acts across space. With this principle, the movement of celestial bodies could be explained using the same framework as terrestrial motion. The orbit of the moon, the path of planets, and the fall of an apple became part of a single system. For the first time, the division between the heavens and the earth collapsed into a unified model. A single set of laws governed all motion, everywhere. Equally significant was the method through which these laws were established. Newton did not rely on analogy or philosophical argument alone. He combined observation, mathematical reasoning, and systematic demonstration. The behavior of objects was not merely described. It was derived from principles that could be tested, applied, and confirmed. To understand motion was no longer to interpret it. It was to calculate it. Given sufficient information, the future behavior of a system could be determined in advance. Prediction was no longer an extension of observation. It became a consequence of law. The implications extended beyond physics. Reality could now be understood as a system governed by consistent principles. This did not eliminate uncertainty. It did not make all outcomes immediately knowable. but it established a framework in which uncertainty could be reduced, measured, and approached systematically. With the publication of Principia, the question that had defined the instability of earlier thought found its answer. Motion was no longer something to be interpreted. It was something that could be known. What made this transformation decisive was not only that the laws worked, but that they worked everywhere they could be applied. The same reasoning that explained the fall of an object could be extended outward across vast distances without losing its validity. Scale no longer imposed a boundary on understanding. The very large and the very small could be approached through the same conceptual framework. This universality carried a profound implication. Reality no longer appeared fragmented into separate realms. Different phenomena could be understood through the same underlying principles. Reality did not require separate languages for separate realms. It required a single language capable of describing them all. Once motion could be expressed through universal laws, the implications extended far beyond the explanation of physical phenomena. A world governed by consistent principles is not only understandable, it becomes manageable. Before this shift, knowledge of nature remained closely tied to observation. Patterns could be recognized, but their application was limited. Without a unified framework, each situation required its own interpretation. What worked in one context did not necessarily apply in another. The absence of universal law imposed limits not only on explanation, but on action. If motion follows consistent principles, outcomes can be anticipated. The trajectory of an object, the movement of a projectile, or the path of a celestial body, these are no longer isolated observations. They become problems that can be solved. To understand the laws governing motion is not simply to observe the world more accurately. It is to intervene within it more effectively. Prediction becomes a form of power. The ability to calculate outcomes allows actions to be planned with increasing precision. This did not produce immediate mastery over nature, but it established the conditions under which such mastery could be pursued. Navigation and engineering began to follow the same logic. Movement across the sea, the behavior of tides, the stability of structures, and the resistance of materials could increasingly be approached through shared principles. Trial and error did not disappear, but it became guided. Failure became more predictable, and therefore more avoidable. Such an assumption changes how reality itself is approached. If the same laws apply everywhere, then the unknown is not something entirely separate from the known. It is something that can, in principle, be brought within the same framework. Exploration becomes less about encountering the unfamiliar and more about extending an existing system of understanding. The unknown does not disappear, but it increasingly appears as a problem awaiting solution rather than a mystery beyond comprehension. Questions that once seemed beyond explanation become subjects for investigation. This does not guarantee success. Nature remains complex. Errors persist. But the ambition changes. Knowledge is no longer valued only for understanding reality. It becomes valuable for acting upon it. In such a world, knowledge is no longer passive. It becomes an instrument through which the future can be shaped. The legacy of Newton, therefore, lies not only in the laws he formulated, it lies in the expectation that reality can be understood well enough to be acted upon. And once that possibility is accepted, it becomes difficult to return to a world defined only by observation. If the universe can be understood through consistent and universal laws, then knowledge itself acquires a new status. It is no longer simply a means of interpretation, it becomes a source of authority. In earlier frameworks, authority was often grounded in tradition, position, or inherited systems of meaning. Explanations of the natural world could vary, and their legitimacy did not depend on precise demonstration. What mattered was coherence within an accepted structure of thought. A world governed by law alters this balance. If motion can be calculated, if outcomes can be predicted, then knowledge begins to justify itself through performance. It does not rely on tradition alone. It proves its validity by producing reliable results. The ability to anticipate and control physical processes becomes a form of evidence. This introduces a new criterion for authority, not who speaks, but what works. Those who can describe the world in ways that consistently align with observable outcomes gain a different kind of legitimacy. Their authority is not symbolic, it is operational. It rests on the capacity to generate predictions that can be confirmed. This shift does not eliminate older forms of authority, but it repositions them. Interpretation remains, but it must increasingly coexist with demonstration. Claims about the world are no longer evaluated solely in terms of meaning. They are measured against their capacity to correspond with consistent principles. Over time, this transforms how knowledge is organized. Disciplines emerge that prioritize method, calculation, and verification. Knowledge becomes increasingly structured around procedures that can be replicated and tested. This approach gradually extended beyond the natural sciences into other domains of social and administrative life. Those who possess the tools to model, calculate, and predict are no longer merely observers. They become interpreters of systems that others depend upon. Their conclusions shape decisions, guide actions, and influence outcomes. Authority becomes linked not only to position, but to the capacity to produce reliable knowledge. This form of authority often operates through systems rather than direct command. At the same time, reliance on structured knowledge introduces new dependencies. Knowledge becomes specialized, expertise becomes necessary. Decisions increasingly rely on those who can navigate abstract frameworks and translate them into practical guidance. This creates a tension. On one hand, systematic knowledge expands the ability to understand and manage complexity. On the other, it concentrates authority in the hands of those who possess the required expertise. This is not a deliberate transfer of power. It emerges from the logic of the system itself. Yet this form of authority remains contingent. Its legitimacy depends on continued performance. Predictions must remain reliable. Models must correspond to observable outcomes. When they fail, authority weakens. Unlike traditional forms of legitimacy, which can endure through belief alone, this form requires constant validation. The transformation initiated by Isaac Newton thus extends beyond the structure of the physical world. It contributes to a broader redefinition of how authority is established, maintained, and challenged. Knowledge no longer simply explains reality. It begins to determine who can speak about it and be believed. The transformation introduced in 1687 did not end with the formulation of laws. It altered how reality itself could be approached. A universe governed by consistent principles encourages the belief that what is not yet understood is not beyond comprehension, but simply beyond current knowledge. The unknown becomes something that can be investigated, measured, and eventually integrated into an existing framework. Understanding becomes a matter of refinement. The world is no longer approached as something that must be interpreted through multiple frameworks. It is approached as something that can, in principle, be made legible. Complexity remains, but it becomes something that can be organized, modeled, and approached systematically. This does not eliminate uncertainty, but it changes its meaning. uncertainty becomes something that can be reduced. The boundary between the known and the unknown becomes a moving frontier. A world made legible is also a world that invites control. The same principles that allow reality to be understood also make it possible to intervene within it. The distinction between knowledge and power becomes increasingly difficult to separate. To describe a system is, in part, to gain influence over it. This does not make reality fully transparent or entirely controllable. Complexity persists. Uncertainty remains. But the expectation has changed. The world is no longer accepted as something that simply unfolds. It is approached as something that can be engaged, shaped, and, within limits, directed. The legacy of Isaac Newton lies not only in the laws he articulated, but in the transformation he helped consolidate. The universe did not become ordered in 1687, it became readable. And once reality could be read, the future no longer appeared entirely beyond reach. From that point forward, the challenge was not understanding the world, it was discovering the limits of understanding itself.